66 million years ago, a colossal asteroid, a mountain of rock and ice, slammed into our planet. The dinosaurs, rulers of the Earth for eons, never saw it coming. Their reign? It ended in a global firestorm and a long, dark winter. Could the same fate be waiting for us? Are we really any more prepared than the dinosaurs were? Or are we just hurtling towards a similar doomsday, armed with defenses that might just be a false sense of security? What if I told you that right now, there are an estimated 14,000 near-Earth asteroids, larger than 140 meters, still undiscovered? These are big enough to wipe out an entire city. We've only found about 40% of them. That means thousands are lurking out there in the darkness, and some could potentially be on a collision course with Earth. Scientists are in a desperate race against time, peering into the cosmos with some seriously advanced telescopes. But is it actually enough? Our first line of defense isn't some high-tech shield, it's a warning system. Meet ATLAS. That's the Asteroid Terrestrial Impact Last Alert System. Developed by the University of Hawaii and funded by NASA, ATLAS is a network of telescopes cleverly placed in Hawaii, South Africa, Chile, and the Canary Islands. These robotic eyes scan the entire observable sky, night after night, hunting for those faint glimmers of light that give away a moving space rock. Think of ATLAS as our celestial watchdog. It's designed to spot the smaller asteroids, the 20-meter kind that could cause local devastation. Remember the Chelyabinsk event back in 2013? ATLAS could spot those just days or weeks before a potential impact. For the larger 100-meter asteroids, objects capable of unleashing destructive force far greater than major volcanic eruptions, ATLAS aims to give us weeks of warning. And it's had some wins. As of early 2025, ATLAS had discovered over 1,200 near-Earth asteroids and more than 100 that are considered potentially hazardous. But ground-based telescopes like ATLAS have a big weakness: the sun. Asteroids approaching from the direction of the sun are often completely hidden in its glare, invisible to our eyes here on Earth until it might be way too late. That Chelyabinsk meteor? No observatory saw it coming precisely because it approached from the sun's direction. This isn't some minor glitch, it's a gaping hole in our detection net. Plus, bad weather and plain old daylight also limit what ground-based telescopes can do. This is where space-based observatories come into play. Telescopes equipped with infrared sensors can operate continuously, totally unaffected by Earth's limitations, and they can spot asteroids that ground systems might miss. They detect the heat signature of asteroids. That means even dark, non-reflective objects glow brightly in infrared as the sun warms them up. NASA knows all about these limitations. That's exactly why they're developing NEO Surveyor, our next-generation asteroid hunter. Scheduled for launch no earlier than September 2027, NEO Surveyor is a space telescope specifically designed for planetary defense. It's going to travel to a gravitationally stable spot between Earth and the Sun, called the L1 Lagrange point, about 1 million miles from us. From that prime location, its 50-centimeter infrared telescope, shielded by a massive sunshade, will be able to spot those sneaky asteroids coming from the Sun's direction, as well as Earth Trojans, asteroids that lead or trail our planet's orbit. NEO Surveyor has a pretty ambitious mission: to find and characterize at least 90% of near-Earth objects larger than 140 meters, those city killers, within its operational lifetime. Finding these objects is actually mandated by the U.S. Congress, and NEO Surveyor is aiming to make some serious headway on that goal. It's designed to take accurate measurements of their sizes, what they're made of, their shapes, and their orbits. All crucial data if we ever need to nudge one out of the way. But even with NEO Surveyor, the challenge is just immense. As of early 2022, astronomers had only located about 40% of these 140-meter-plus objects. While discovery rates are getting better, with NASA-funded surveys finding about 500 such asteroids every year, hitting that 90% goal is a monumental task. And that only covers the 140-meter and larger threats. There are likely tens of millions of smaller space rocks, between 10 and 20 meters, that could still cause significant local damage. While we're waiting for NEO Surveyor to get up and running, automated prediction systems like NASA's Sentry system and the European Space Agency's NEODES are constantly scanning asteroid catalogs. They analyze orbits and predict potential future impacts, flagging objects that need a closer look. These systems are vital, but their effectiveness is totally limited by how complete our detection is. You simply can't predict the path of an asteroid you haven't found. And the current system's overall success rate for detecting an incoming object, especially the smaller ones, is pretty sobering, sometimes estimated to be as low as 1%, depending on a lot of factors. So, we've got telescopes scanning the skies, and more advanced ones on the way. We have systems designed to predict impacts. Sounds pretty reassuring, right? But here's where the exposed part of our story really comes in. How effective are these systems, really? Are they the impenetrable shield we're all hoping for? The sheer number of undetected asteroids is a glaring vulnerability. Thousands of city-killer-sized objects are still out there, their orbits completely unknown. And while a lot of effort is focused on those 140-meter and larger threats, what about a 50-meter asteroid? An object that size, like the one thought to have caused the Tunguska event in 1908, could obliterate a city and cause widespread regional devastation. It wouldn't cause a global catastrophe, but it would be an absolutely unprecedented disaster in modern human history. Then there's the warning time. Atlas might give us days or weeks for certain sized objects. But what if a large, previously unknown asteroid is discovered on a trajectory that gives us only months, or maybe a year? Our current deflection technologies, our high-tech shields, often need years, even decades of warning to actually work. And it's not just about finding them. We need to know what they're made of, their exact size, how they spin. This characterization is crucial for planning any kind of deflection mission. NEO Surveyor will help with this for the objects it finds, but there's a massive backlog and a whole universe of unknowns. What's more, the financial resources dedicated to this global threat haven't always matched the scale of the problem. While missions like NEO Surveyor are a significant step, that 2005 U.S. congressional mandate to find 90% of NEOs 140 meters and larger by the end of 2020, it wasn't met, largely due to funding limitations. This delay means we've had more years living with a higher degree of unknown risk. International cooperation is another huge factor. Asteroids don't exactly recognize borders. China is ramping up its own planetary defense efforts, developing the China Compound Eye radar array to track asteroids and planning an asteroid deflection test mission. They're aiming to test an asteroid deflection system around 2027. This is a positive development because a global threat requires a global response. But are these efforts coordinated enough? Is data sharing and joint planning robust enough to handle a crisis that unfolds rapidly? The recent scare with asteroid 2024 YR4, which was initially given a concerning, albeit small, chance of impacting Earth in 2032, really highlighted both the strengths and weaknesses of our current systems. Atlas detected it, and observatories worldwide quickly began tracking it. The initial probability of impact fluctuated, and even rose for a bit, causing significant public and scientific attention, before more observations thankfully ruled out a significant impact threat to Earth. While this was a successful test of the detection and follow-up process, it also served as a stark reminder of how quickly a new threat can pop up and the anxieties it can create. It exposed just how reliant we are on continuous observation to refine orbits, and how unsettling that initial uncertainty can be. Okay, let's say we find a dangerous asteroid with enough lead time. What then? Can we actually stop it? This is where our high-tech shields come into play, primarily the idea of deflection. The most famous example is NASA's DART mission. That's the Double Asteroid Redirection Test. In September 2022, the DART spacecraft deliberately slammed into Dimorphos, a small moonlet orbiting the larger asteroid Didymos. The goal wasn't to destroy Dimorphos, but to nudge it, to change its orbital period around Didymos. And guess what? It worked. DART successfully altered Dimorphos's orbit by 32 minutes, proving that the kinetic impactor technique, basically hitting an asteroid with a spacecraft, is a viable method for changing an asteroid's path. This was a landmark achievement, humanity's first successful test of planetary defense technology. The European Space Agency's Hera mission, planned to launch in 2024 and meet up with the Didymos system around 2026, will conduct a detailed crime scene investigation. Hera will study the aftermath of DART's impact, measure Dimorphos's mass precisely, and examine the crater. This will give us invaluable data to refine our understanding of how effective kinetic impactors are. This international collaboration, known as IDA, Asteroid Impact and Deflection Assessment, is crucial for turning this experimental success into a reliable defense strategy. But kinetic impactors have their limits. They're most effective when you have a lot of warning time. Years, preferably decades, to make a tiny nudge that translates into a big miss over a long distance. What if we only have months? Or what if the asteroid is exceptionally large? For those bigger threats or shorter warning times, more drastic measures might have to be considered, including the nuclear option. Concepts like the Hypervelocity Asteroid Intercept Vehicle, HA, propose using a nuclear explosive device to either deflect or disrupt a threatening asteroid. A subsurface nuclear detonation could deliver a much larger force than a kinetic impactor, potentially breaking up the asteroid or significantly altering its course. However, this approach comes with immense political, technical, and safety headaches. The idea of detonating nuclear devices in space, even for planetary defense, is loaded with challenges. Other research suggests that multiple small impactors might actually be more efficient than one single large one, especially for asteroids with unusual shapes or those rubble pile compositions. China is also exploring deflection techniques, with plans for a kinetic impact test of their own. So the shields do exist, at least in concept and very early testing. But their readiness and how well they'd work against a wide range of threats are still very much in development. We have one successful small-scale test with DART. We don't have an off-the-shelf system ready to deploy against a massive short-notice threat. The idea that we have some impenetrable asteroid shield is, frankly, science fiction at this point. We're building the tools, but the toolbox is far from complete. We've looked at the hunters, the advanced eyes like Atlas, and the upcoming NEO Surveyor, scanning the cosmic shooting gallery. We've examined the high-tech shields like the DART mission's kinetic impactor, and the more extreme options still on the drawing board. So the big question remains, are these efforts enough to stop a major impact, or are we just delaying an inevitable doomsday? The truth is, it's complicated. Our planetary defense capabilities have advanced enormously. We are no longer as blind as the dinosaurs were. We can detect many threats, and we've demonstrated a basic ability to deflect a small asteroid. That's a monumental step. However, the exposed elements are significant. Many potentially hazardous asteroids are still undetected, particularly those that could cause regional city-level devastation. Our detection systems have blind spots. Our current deflection technologies require long lead times, which we might not always have. And for the truly massive, planet-killer asteroids, while exceedingly rare, our options are still largely theoretical and untested on a grand scale. We aren't just delaying an inevitable doomsday in the sense of passively waiting for the end. We are actively working to understand the threat and build defenses. We are buying time. Time to find more asteroids. Time to develop better and faster deflection technologies. Time to foster international cooperation, and time to prepare comprehensive response plans. Planetary defense exercises, like those conducted by NASA, simulate impact scenarios to test our readiness and decision-making processes. These are crucial for finding the gaps and improving coordination. But preparedness is never absolute. There will always be an element of risk we can't completely eliminate. The universe is a vast and dynamic place. The challenge is to reduce that risk to a level we can live with. Code Red, Earth's Asteroid Defense Systems Exposed, paints a picture not of imminent doom, but of a monumental challenge being met with incredible human ingenuity and determination. Our shields aren't perfect yet, and the cosmic threats are very real. But unlike the dinosaurs, we have the ability to look up, to understand, and to act. Whether we're truly safe depends on our continued vigilance, our investment in science and technology, and our willingness to work together as a planet to protect our shared home. The question isn't whether we can stop doomsday, but whether we will do what's necessary to try. The clock is ticking. Thank you for listening to my thoughts. and for coming along with me on this little journey. Have a beautiful day. Goodbye.